Thanks so much. Thanks everyone for attending. I hope you've had a good lunch and a nice networking. So we're going to restart our session here with April Joubert. April is animator and video producer at Smithsonian Astrophysical Observatory with the presentation Data-Driven Modeling, using scientific 3D data to create and work in 3D prints. Take it away, April.
All right, can everyone see my slideshow?
Yes, we can.
Great. All right. Well, hello. I'm April Joubert. And as Elaine said, I'm the animator and video producer for NASA's Chandra X-ray Observatory. So I'm going to talk today about gathering data with the Chandra telescope and using that data to teach astronomy and physics, which for me has included the exploration of 3D printing some of Chandra's videos. Real quick. So Chandra's image processing team uses data collected from deep space to create 2D images, which you can see here. And those help us to explain some very weird phenomena. I started working for Chandra back in 2002 as a 3D animator and a storyteller, using Chandra's images as a jumping off point to create videos that teach about astronomy and physics, and some of these far out phenomena like black holes and supernova explosions. And then something exciting happened right about the time when the Smithsonian Institution was 3D printing Obama's head. We were wondering how we could start using similar technology. Some astronomers were figuring out how to collect 3D data on objects that we were already studying in 2 dimensions. So we started to explore our options for creating 3D prints to represent astronomical data. So this has led us down a rabbit hole of finding different ways to represent and share data collected by the Chandra X-ray telescope. So let me back up and tell you a little bit about the Chandra X-ray telescope. It's a sister satellite to Hubble and James Webb. It's in orbit around Earth and has been since 1999. So we're almost at our 25th anniversary, which is very exciting. It's greatly outlived its expected 8 years of operation. And so you can see this first image here is an illustration of the Chandra telescope, and it collects data from X-ray photons, which you can see in the second illustration, and we turn that data into images in the third image here to learn about high energy processes that are happening regularly in space, giving off X-ray light and therefore phenomena that we couldn't see without the use of instruments like Chandra. So here's an animation of Chandra in space. It's about the size of a school bus. There are sensors in the tail end that just went by us there, and this long tube is mostly empty space. And X-ray photons hit the front of the spacecraft here in these concentric mirrors, and they're focused onto the instruments at the back, 10 meters away, which record their positions and energy levels. Here's a schematic representation of the mirrors and the way that X-rays enter the telescope. And they are glanced off at these angles and focused onto the sensors at the back of the telescope. This is a simplified animation. The result is not a complete picture as is depicted here, but a chart of the data. So the data is then processed into an image with different colors representing features, very much the way a weather map uses color to show temperature or pressure data. And the resulting image here is the X-ray data, represented as a color map of supernova remnant Cassiopeia A. So Cassiopeia A was a star. It exploded about 350 years ago. In 1680 AD, somebody who was studying that part of the sky in the constellation Cassiopeia looked up and saw something different. And what we see in the X-ray image is energy in the form of X-rays. There's the explosion there. Coming toward the Chandra telescope, and that's coming from the material being expelled outward after the death of the star Cassiopeia A. So X-ray photons enter the telescope and are recorded as data, or ones and zeros, and it's kind of like a camera taking a picture, but recording the information as positions and the time that these packets of energy hit the sensors and their different energy levels. And it shows, so this table here shows the frequency and intensity of the photons hitting the telescope. So astronomers use software to convert the information into a visual map in black and white using brightness to show varying energy levels or the frequency of the photons hitting the detectors. And those are displayed as XY coordinates just as they hit this little detector at the back of the telescope. This is DS9. It's a program that image processors use to manipulate the contrasts, etc. And then they add color. And this here was actually the very first image that was processed from Chandra data back in 1999, right after launch. So the colors added, and in this case, the energy levels were broken up into 3 colors. So we have red for the lower energy cuts, green in the middle, and blue in the higher energy cuts. And that's all within the X-ray wavelengths or bands of energy. And that gives us our weather map, so to speak, of energy. And scientists can use spectroscopy to determine which elements are present in the different areas of the object, iron, oxygen, calcium, etc. So sometimes color is used to differentiate between different elemental signatures. So we can map out the elemental composition of the star as it turns itself inside out in the explosion. So we can tell a lot about how the star lived and died, what it was made out of, how massive it was, how it's changing as its elements move outward to eventually recombine as other things. And I just threw in this time lapse of the data over the years to show that we have been studying it for almost 25 years now, and it shows that this is not a static object. This is a growing outward of an explosion of the remnant. So we have all this great information, but it's still a 2-dimensional image, as though Cas A is a projection on a 2D plane hanging in space. But this star, when it exploded, it expelled, and it's still expelling material and energy in 3 dimensions. So how do we look at it in 3 dimensions? We can't approach it and look at it from different angles, walk around it. It's 11,000 light years away from us. It's enormous, and it's 50 million degrees Celsius. We couldn't even get close to it. So we are able to use something called the Doppler effect, which I think we're all familiar with as it applies to sound waves. Think about a car driving towards you and you're standing on the sidewalk. Well, if you're sitting in the car, you hear the hum of the engine as a constant pitch. But if you are sitting on the sidewalk and the car is coming towards you and then passes you and moves away from you, the sound waves coming from the hum of that engine are actually getting compressed as it comes towards you, as the car moves, and then the opposite happens as it passes you. So you're hearing a change in pitch as it applies to you standing there. So let's consider the Doppler shift applied to other wavelengths. So for example, the visible spectrum of light waves that we can see, we do talk about stars with redshift as something moves away from us. The wavelength of energy that we detect is moving further into the red end of the spectrum. And blue shift is the opposite. It's things that are moving toward us, move further into the blue end of the spectrum. So the same concept can be applied to other forms of electromagnetic radiation. So in this case, X-rays. And scientists working at MIT, Tracy Delaney, studied Cassiopeia A using Chandra and Doppler shift data to add that z-axis to the already existing x and y axes. And she shared her data with us, which looked a little bit like this. So now we have information telling us where the energy exists along the z-axis as well. And we can project that data in 3 dimensions using software and creating this digital 3D model of Cassiopeia A. And so I've been working with programs like Maya and Blender to try to optimize this model for 3D printing. And there it is, one of the first times we printed it on our little MakerBot 3D printer. And then at one point, we even had a powder printer. That was a bit of a full-time job, but we got a few good full-color prints out of it. We also got some really terrible prints. I just wanted to show a few quick slides here of some of the problems we ran into just trying to learn how to do this. This is a print of Cassiopeia A that didn't finish. This is clogged extruders, which just built up and kind of destroyed some pieces of machinery here. That one should have stopped. So anyway, it was a huge learning curve, and I'm an animator. I work with models for the screen, and that's very forgiving. Now building actual objects, I had a lot to learn, such as dealing with things like non-manifold geometry, which hadn't been in my vocabulary before, slicing software, decimating models to keep file sizes manageable, especially for third-party services to make prints for us, which I eventually ended up doing because of things like this. Anyway, there's always the question of how much we can manipulate this data in order to make it presentable. And that is something we discuss all the time. So you can see here, this is a slightly modified version of the data that we got from the scientist. And we've got all these floating shells and very thin, shown in purple here, these very thin jets of material. And my first inclination was to let's just delete everything that's not attached to the main part of this model. And that eliminates the problem. But then it turned out that this data was actually really important. The little skinny purple jets that you see there are something that we hadn't seen before without the Doppler data, with just this two-dimensional image. And that actually told a bigger story about the explosion. And what scientists think is that Cassiopeia A exploded twice. And the first explosion was this roughly spherical explosion with nothing in its way. And then the second time it exploded, material and energy kind of burst through the first explosion, and it created these kind of jets in a couple of different directions. And so that was a piece of the story that we really wanted to tell. And so we had to figure out how to print that. This was kind of my solution to that. You can see that the long, skinny purple jets are a little bit fatter, and I've connected them along with some other little blobs with these little gray areas that aren't real data. So that was kind of our happy medium. Let's take this data and try not to destroy too much of it, but let's get it to a manageable print. And we still had issues with, they're still pretty skinny. They're still sticking way out there from the original model. So we were getting a lot of breakage. And then we decided to work with magnets. This is one of our color prints from the powder printer. And I thought it would be a good idea to print the jets separately and work with some glue in post-processing and try to glue on these tiny little magnets. And this is what it looks like put together. And so that actually inspired the use of magnets to troubleshoot another problem, which has to do with the perception of this object. So this hard plastic blob doesn't allow us to see or touch the interior of this spherical wave of material. So I started cutting this model in half and adding magnet holes and more gluing, and hoping that the magnets didn't flip in the process and that we could actually stick it together. I have to say though, snapping this thing together and opening it up to reveal the shape of the interior was very satisfying. And so that leads me into perception. So the danger of printing a supernova remnant as a solid object is the potential of shaping the user's perception of the object we're presenting. So in reality, this is hot, invisible, ethereal gas and energy that's changing as we speak, and we have the data to back that up. And so here I am producing these hard plastic static objects. So I don't know the right solution to that, but I try to always remind people, just to reinforce the data, that this model is just another representation of something that is in fact invisible to start with. All of our representations of this object are modifying the data in some way, because this data is invisible, it's hot, it's far away, it's enormous, it's changing continuously until one day it will dissipate and not be detected at all as a cohesive object. And I think the cross-sectional version of the model also helps to engage that conversation. And I also think this version of the model makes the interior of the shockwave more accessible and hopefully enhances our understanding of the very phenomenon of supernova explosion. So the 3D models are just one piece that we're exploring. in order to bring astronomy education closer to being accessible to everyone. So not everyone can see our images, right? So we're trying to create resources for blind and visually impaired audiences. We started creating tactile plates, which you see in the second image here, along with our image releases. And the process we used was developed by Nick Bond, a blind astronomer in the UK, who created a plugin for Blender to import 2D images and use their brightness levels to create relief maps that can be printed for tactile learners to experience the images. So the software and plugin are free and very straightforward to use. It's been really great to work with Nick. And we're also continuously gathering feedback from the blind and visually impaired community. So we work with a blind amateur astronomer in Canada for testing our resources, and I sent her some of these tactile plates for testing, which led us to make a few changes, and I'll show you one here. This is, I don't know how well viewers are going to be able to see this, but this is a tactile plate of Sagittarius A star, which is the black hole at the center of our Milky Way galaxy. And one point that she brought up was, I don't know if you can see, but the G especially is kind of curvy and has a lot of little extra lines on it. And that's something that I hadn't thought of before. The font is actually important. And so I went through a whole bunch of different fonts trying to find the font that exists with the least extra curves and letters. And I still haven't found one. I welcome any suggestions. I still haven't found one that I like. And I've started to create my own. So hopefully that will solve that problem. I'm interested to see what she thinks of that one. And so now we have this 2D image, we have our 3D model, we have our 3D tactile plate, and to that we also have added some audio resources to increase accessibility and inclusion in our data. So I'll just play you for a second. This is the sonified version of the 2D image, and this is just using sound instead of color to represent the data. And this is actually a composite of the sound and the imagery. And I also record visual descriptions of each image now as well. The second image resembles a disk of electric blue light, purple colors, glowing white clouds, and red and yellow flames, dotted with glowing orange smoke. So things like that. I just want to run through a few other examples. I wanted to highlight Cassiopeia A because that's kind of our poster child. And but we have a growing number of objects in our 3D collection now, all of which we make available as 3D files and as the basis of several educational activities as well. This is Supernova 1987A, and you can see this in some of its different iterations. Here it is about to be printed. Here it is being printed on that MakerBot. Kind of a not our best try. Here's a better version of that. And we also use it in a tutorial for students as an intro to 3D modeling with Tinkercad. And so I'll provide links to this activity and others in a moment. This is the Tycho supernova remnant being printed, and this is what the 2D image looks like, and also a version of the blast wave showing the internal structure of the material. This is V745 SCO, and this is a nova. Here I am printing it very quickly on our Ultimaker. And this one we were experimenting with printing in 2 colors so that we could show the ejecta, the actual material being blown off this, and then the shock wave that forms around it. I showed this earlier. This is the Crab Nebula, which you can also see has some very thin jets. This is a rapidly spinning pulsar with these bipolar jets, and these things are breaking off all the time, but this one has survived so far. That's the 2D image and also an image of the 3D print. Eta Carina is another explosion that exploded in 2 poles. Here it is as 3D. This is IC443, or the Jellyfish Nebula, which was a lot different from some of these other ones, and the 3D print. here's the pillars of creation. You may recognize this from a recent James Webb release, but this is pre-James Webb data, and I did not create this model. That was one that somebody else made. Here's U Scorpii, which is another nova with the star kind of off center, and we're working on that one, trying to print it in various colors and cross sections. Just real quick, I wanted to also show you that we're also using these 3D objects in VR and AR applications, and we've tried displaying them in many different ways. Here's a hologram so that we can show it to people during pandemic times without having to pass around models and touch them. And we even have a Lego activity that allows you to build a representation of CASA using Legos. We've recently partnered with Lego for the Blind to create text-based instructions for translation into Braille as well. So I haven't received any feedback yet from any DVI users, but I'd love to know if anyone has used this activity yet, and it was fun for me. So thank you, that's about all I have to say. I've got some links up here. You can get to, I think, pretty much any of our educational activities that I mentioned through these links. So I'll keep that up and try to field some questions if there are any. Cloud print cores are the worst.
So much, April. We've got some questions for you. That was a really interesting presentation. I've never seen the representation of like supernova and nebula and things like that, like only on like Star Trek and things. So it's pretty amazing. So some of the questions. So one question from Kimberly saying, this simulation approach has paved the way for what we are seeing with the James Webb Telescope as well. And are there differences?
The difference is James Webb is working in the infrared spectrum, and we work in X-ray with Chandra, but there's a lot of crossover. And we've actually released some images where we're layering our images on top of the James Webb to kind of get a more full picture of what we're studying. I'm not sure if that answers that question.
Yeah, I didn't realize that the two what do you call those vehicles are detecting two different kinds of things. So that was a pretty useful piece of information. Here's another question.
Yeah, we often look at the same objects that other telescopes are looking at. For example, we've worked hand in hand with the Hubble Space Telescope, which it'll look at this in the visible spectrum, and we'll look at the same area of the sky in the X-ray, and then maybe an infrared telescope will give us more data, and it just kind of opens up the science.
Yeah, exactly. The other part of the spectrum that you're not looking at. So another question is, can you give examples of what capacity the visually impaired have used the models for?
Sure. Well, we do work with a lot of schools that work with visually impaired, and we have kits that we can send to them that have some of our models. And so they use them the same way that schools would use our images to talk about supernovas or black holes, or we do a lot of supernovas. We own pulsars, and those things so far are what we've been printing. And so instead of showing a class an image or showing an image at a presentation, if there are visually impaired people, things are handed around and touched.
Great, and probably our last question for you. What was the Blender plugin that you mentioned?
Okay, so that is called Tactile Universe, and let me see if I can find that link real quick. I think it's tactileuniverse.org. Yes, if you go to tactileuniverse.org, the plugin is available under models and resources. And,
yeah, I guess people can also find that in the chat, or if you copy and paste that, you can put it in the chat and people could get that right away. So yeah, that was super amazing, interesting visualization, which I never thought of. But yeah, you're involving a whole nother sort of like group of people who would be otherwise disconnected from this kind of experience.